Drive past a sprawling commercial wind farm on a particularly stormy, blustery day, and you might see something that makes absolutely no sense. The wind is howling, and the conditions are perfect for generating extraordinary amounts of power. Yet, if you look closely, you will see that dozens, sometimes hundreds, of these colossal turbines are completely dead still. These machines remain fully functional, deactivated only by an encrypted command from a control room hundreds of miles away. We spend billions of dollars building these multi-million-dollar machines because the world desperately needs energy. So why, when the fuel is free and blowing at gale force, would anyone intentionally command a wind farm to stop making power? To understand why we throw away free energy, you have to look at the illusion of electricity. Plugging your phone into a wall socket feels like tapping into a vast, waiting reservoir of power, like turning on a faucet connected to a giant water tower. But the electrical grid has almost zero memory and almost zero physical storage. The electricity powering the screen you are watching right now was generated mere milliseconds ago. This data visualization shows a highly sensitive scale, perfectly balancing energy input against real-time consumption. Because we cannot store power at a continental scale, supply and demand must match perfectly every single second of the day. If 1 million people turn on their ovens at once, a power plant somewhere must instantly push the exact equivalent amount of power into the wires. Humans are generally predictable. Grid operators know exactly when we wake up and when we go to work. They balance the grid by ramping traditional gas, nuclear, and coal plants up and down to match our routines. While humans and traditional plants operate on predictable schedules, wind operates entirely independently of human demand. Imagine it is 3 in the morning. The cities are asleep, factories are powered down, and human demand for electricity has dropped to its absolute daily minimum. Suddenly, a broad weather front moves in. The wind accelerates. Across thousands of square miles, offshore turbine blades begin spinning faster and faster, instantly dumping hundreds of megawatts of unconsumed power into the sleeping wires. But nobody is using it. Without battery storage, unconsumed energy cannot pool. It is a physical force. When the power supply outpaces human demand, that unconsumed energy instantly converts into physical pressure within the network. This pressure is known in the electrical world as frequency. In North America, the entire power grid is engineered to operate at exactly 60 hertz. It is the heartbeat of the grid, meaning the alternating current pushes and pulls exactly 60 times a second. Every physical machine plugged into the wall is engineered to run at exactly that rhythm. Pushing too much power into the sleeping grid causes this frequency to spike, turning free energy into a force that can physically tear infrastructure apart. The frequency creeps from 60 Hz to 60.1, then 60.2. While a laptop charger might not notice, the heavy physical infrastructure of the modern world feels the stress immediately. At 60.5 Hz, large industrial electric motors start spinning faster than physically designed to. Their internal friction increases, and they begin to dangerously overheat. As frequency approaches 61 Hz, the real danger shifts to industrial-scale step-up transformers at substations, the hubs acting as the grid's circulatory system. Inside these heavy steel tanks, huge copper coils are wrapped in insulating paper and submerged in liquid mineral oil. When frequency spikes, the saturated magnetic core generates rogue electrical currents. Heat skyrockets, boiling the oil and degrading the paper until the transformer explosively melts. To prevent this physical destruction, heavy-duty automated safety relays are installed throughout the network. If they detect a severe frequency spike, they violently sever the connection to protect the transformers. But the power traveling down that severed line does not disappear. It routes itself to the next available power line. Now that second line carries its normal load, plus the crushing new load. It instantly overheats, relays trip, and combined power is forced onto a third line. This cascading failure moves at the speed of light. In a matter of seconds, a surge of completely clean, renewable wind energy in the middle of the night can trigger a multi-state blackout. This chain reaction is what grid control centers are designed to prevent. Deep inside highly secure regional rooms, dispatchers monitor the live heartbeat of the grid in real time against incoming weather fronts. When the imbalance becomes severe, an economic anomaly happens. The wholesale price of electricity drops below zero, and grid operators have to pay neighboring grids to take the excess power. When no one else can take the power, the operators have one choice left. They execute curtailment, the intentional throwing away of free energy. The control room sends a heavily encrypted digital command out through the network. This signal travels at near light speed through fiber optic cables, woven into the tops of the transmission towers, shooting directly to the wind farm. The digital command is incredibly simple: stop. But bringing a spinning 100-ton machine to a physical halt in a violent storm is a formidable physical challenge. You cannot just slam on a brake. Applying mechanical friction in 40-mile-an-hour winds generates sheer kinetic force, instantly igniting the brake pads, and risk burning the entire tower to the ground. Instead, the turbine has to fight the wind using aerodynamics. Inside the central hub sit heavy hydraulic rams and heavy-duty electric motors attached to the base of each individual blade. This diagram shows a process called pitch control. When the signal arrives, internal motors activate. They physically rotate the towering 150-foot fiberglass blades along their axis, turning them perfectly flat against the oncoming storm. The aerodynamic lift is instantly destroyed. The wind stops pushing the blades and slides uselessly past them. Deprived of force, the 100-ton rotor safely slows to a crawl, so a mechanical lock can hold it steady. Those stationary blades represent the grid's emergency brake, a safety mechanism discarding power to keep the modern world intact. The next time you see a dormant wind farm in a storm, you are watching an invisible mechanism protecting the system from tearing itself apart.